Fortunate today to have three distinguished guests, and I'd like to introduce them to you right now. To my left is Dr. Toni Churg, and she happened to have worked at the University of Chicago, which is the first place in the United States where a sustained nuclear reaction was created. And to her left is Professor James Warf. Now, James has had the distinction of working on the Manhattan Project during World War II, when the United States developed its first nuclear weapon. And to his left is Dr. Jack Jennings. And he has a history of working in the aerospace industry and the development of the delivery systems which were designed to deliver this nuclear weapons. And I want to go right into an educational thing for the public today. Okay? Jim, you brought along some samples of radioactive material, and I'd like to see if you could please demonstrate to us what they are, just to get us a little bit familiar with the materials.
Yes. Let me first just show the ores here of uranium. This element was discovered by a German chemist about the time of the American Revolution. And 100 years later or so, a Frenchman discovered this phenomenon we call radioactivity. Here is the principal ore of uranium. Just looks like a chunk of coal.
Could we take that out?
Yes. And here is the second ore of uranium.
Can we take them out of the containers?
I wouldn't, because they are radioactive and I don't want to get dust around the place.
Oh, all right.
So they're not very attractive black substance, but a rather pretty yellow-orange material.
Okay, let's see how hot they are.
Now, in order to measure the radioactivity, one of the common instruments is a Geiger counter. I have here one such instrument, which is of a simple, inexpensive type. This is the probe, and the electronics are here. Now, this one is rigged up so that the radiation that comes out into the Geiger counter registers both on a needle and by sound, so you can hear the clicking. What we hear now is in part the background radiation, cosmic rays coming in from the sun and other stars. We get it close to the ore, and you see the needle goes off scale and the sound becomes very intense. If we take some lead and put on top, well, it's still, we get a count, but it's weaker, you can tell from the decrease in the sound. Finally, here is about 1 pound of uranium metal. Now, uranium metal, when pure, is shiny, it looks like steel, but this is covered with a black oxide. This little piece is 1 pound, and you can see too that it is very radioactive. Not near as much as dangerous materials, or I wouldn't be holding it, but it is a common radioactive material.
Jim, let me ask you a question. If I were to, that little black rock in that smaller vial, if I were to put that in my pocket or in my wallet and carry it around for 3 months in my chest, my jacket pocket, would that be harmful to me?
Not particularly. It'd do a little bit of harm, but not much.
Jim, what is it? Is that a dosimeter there?
No, this is a little sample of radioactive material. It's actually Cobalt 60 in here. Cobalt 60 emits gamma rays. Now, let's talk just a little bit about what is the origin of the radioactivity. Today, it is known that each atom has a nucleus, small and heavy. 99.9% of the mass of the atom is in it, and then surrounding it is a cloud of electrons. And what happens is, when you have millions and millions of these nuclei, statistically, they decompose. They kick out an alpha particle, which is the nucleus of helium, or a beta particle, which is just a fast electron, and then there are other types, and finally gamma rays. And these gamma rays then are constantly coming out at a definite rate. The rate of decomposition is measured in terms of time, half-time or half-life. And I think we'll give a little demonstration of this here using, you might say, the kitchen approach.
Oh, one other thing, Jim, is that device is measuring the gamma rays, right?
This measures
Strictly?
both gamma and betas. The alphas not go through this particular probe.
Oh, it does. That does.
Yes,
Betas can.
Betas too. So let us say that these beans here represent a pile of radioactive material. Now we wait a certain length of time, suppose in this case a year. Half of these will have decomposed. Just half. So we say the half-life is 1 year. What happens is that they become another material. Let's say that's represented by the white beans. So if this material is not radioactive, well then this its parent just decreases every year a half. Say we have 100 pounds at the beginning. After 1 year there's 50 pounds of this and about 50 pounds of the white material. Another year 25 pounds, another year 12.5 pounds, another year 6.25 pounds, and so forth. Gets lower and lower and lower.
This disappears but changes into this.
Changes into the white material. In some cases the product is itself radioactive. It might undergo alpha decay or beta decay or gamma decay, and it produces then still another kind of element, represented say by the green lentils here. After one half-life is gone, an equal number of particles of the green ones come. Each substance, the brown, the white, the green, has its own characteristic half-life.
So what's the importance of counting beans now?
Well, it's only to indicate that each substance, each radioactive substance is characterized by a certain period of time when half of it undergoes radioactive decay.
Okay, now let's talk. Let's take a look at this in terms of what we hear in the news. If this was from what's a local reactor everybody knows, San Onofre? If this was spent fuel rod material, this much, actually, this much mass of spent fuel rod material, these brown beans here. Okay, that much. Is that dangerous, A? And B, how long would this survive?
If you just take it fresh out of the reactor, that amount would be an extremely dangerous amount, even at this distance. During this program, I imagine we would all get a fatal dose of radiation.
Over a half-hour period,
yes,
we'd have a fatal
something
dose.
like that.
Okay, now what if I took one bean like this and left it in the center of the room?
Are you talking about
No, this amount of mass.
Oh,
this amount of mass.
all right.
And left it in the center of the room.
Yes.
Would it have, over the period of a week, would this travel?
If you're near it at all, you would be a week. Of course,
Well, how far away would I have to get? What if I was in front of the building?
That would be probably safe then.
Okay, so you're
More or
looking like
less
a small radius of effect.
See, all these questions, the amount of dose is the important thing,
Right.
and over amount of time.
Okay, well, how long will that survive in that condition?
Well, what is done in commercial A, they take the fuel rods out of the reactors and store them underwater to absorb the heat. The water gets hot and it's cooled in a radiator. The steam comes up. You've probably seen that. After 10 years, 88% of the radioactivity has decayed.
So you have hardly any radioactive...
8% is left, 12% is left after 10 years. Now, that, however, is not a single radioactive substance. It is a mixture of 50 or 60, and it does not go down. It does not show the same laws of decay. Each isotope does, each element does, but in general, it's a much more complicated decay because it's a mixture of substances.
Spent fuel rods are a complicated mix of things.
Well, and there's lots of factors involved. But if I started with this much material from a fuel rod, how long would you want to isolate it before you'd allow somebody to get within 10 feet of it?
Well, I would say 500 years at the very least, and probably 1,000 or even 10,000.
I think also there's a big difference in how you treat the fuel rod, whether you open up the container
yes, of course.
and empty spill the beans, as it were, or leave it intact. I think that has an important significance as far as the reprocessing.
To leave the cladding on it.
Yes, not open them up. The only ones that are opened up are the military reactors giving material to isolate plutonium to make weapons.
All right, but commercial materials are left cladded or encased in their tubes.
That's right.
Okay, so if we're talking about...
They contain, incidentally, more percentage of plutonium than the stuff that comes out of the military reactors.
Right. The military gets its plutonium based
Also
on
from reactors.
From commercial materials.
No, not from commercial materials.
That's illegal, isn't it?
That's illegal, although it has been done once or twice anyway. The trouble is, see, there are several isotopes of plutonium. The military likes plutonium-239. The longer the material stays in the reactor, it's true the more economical the reactor is, but the more plutonium-240 is produced, and that is not suitable for bombs. So the military reactors expose the material only a few months and then take it out.
So you're saying as the material stays in commercial use, they lose the 239, it turns to 240.
That's explained well in this book here.
Right. Go ahead.
Can I put a plug for one of my favorite topics? You know, there is a saturation of plutonium, even if, as far as our military is concerned. But there is a rationale for reopening the reactors at Savannah River. In many people's eyes, we need to make more tritium, and that's another component of the bombs that is an isotope of hydrogen. And
what's the rationale?
The rationale is that tritium has a short half-life. A little bit of tritium is put in bombs, essentially to enhance the bang for the amount of mass that's in the bombs.
It's act as an amplifier.
Great, and the tritium then will decay according to these principles with a half-life of 12 years. So the bombs don't have an indefinite shelf life. Well, so they claim that they have to replace the tritium in the bombs.
Well, but you said the rationale. You mean the justification?
Correct.
It's not rational.
Thank you. Okay, but I mean that's one of my pet peeves is that people are taking it on faith that we have to replace this tritium when in fact what we should be doing is making the arsenal smaller so that the tritium can keep pace. So if we keep shrinking the nuclear arsenals at the rate that the tritium is decaying, in 100 years we might be down to a reasonable size. I mean, there's plenty of tritium there.
If we want to be safe sometime sooner than that, then we would have to beat the rate of disappearance of the tritium as far as reduction in the stockpile is concerned.
So the development of the tritium and the use of the tritium in nuclear weapons was that hydrogen bombs, which are what, 10 or 100 times more powerful than atom bombs, 1,000 times more powerful than a Hiroshima bomb, that's not good enough. So they put tritium in to get a little bit more punch.
That's right.
So, I mean, is this a question of how thoroughly or how fast we could destroy something?
No, I think it's more a matter of getting a lot more bang for the same mass now. I mean, you can get a 100 Hiroshimas, 1,000. How many Hiroshimas do they have on the MX now?
One MX missile?
One MX missile. I mean, you get a lot for about the same mass.
About 20 or so.
20 Hiroshimas on one missile.
Oh, no, that's of the small bombs only. A single big bomb can be far more than that. But the big bombs, we're digressing a bit.
Well, I know, but it's very interesting.
The huge bombs are not as effective militarily as half that power and twice the number.
Right, because you get it strategically.
Less overkill.
Right.
So the big 1 megaton bombs have more or less disappeared to be replaced by 2 half-megaton bombs. But that's
Kind of like, I kind of get a picture
yes.
of when I go into the market and you see these little butterscotch pudding in a six-pack, as
Yes.
opposed to getting a big can of it.
But-
and 1 megaton is far from the biggest bombs that were made.
Right. I want to get back, though, to the commercial nuclear use. So if this was spent fuel rod material, you would like to keep it isolated for anywhere between 500 to 5,000 years. You wouldn't want somebody to come within 10 feet of it.
No.
Wouldn't be good for his health.
No.
Okay, now I do want to get into another subject, which is what the government or the Nuclear Regulatory Agency is calling below regulatory concern. In other words, when people work in the nuclear industry, they wear clothes. There's pumps, there's pipes, there's things around nuclear reactors that are radioactive, but not like the radioactive material in the reactor. And this they're trying to call it below regulatory concern, or low, what do they call it? Low energy radiation?
Low-level waste.
Low-level waste. Okay, so what is low-level waste, and how dangerous is it?
It's even below the limits for the low-level waste. It's a new category that has been created. To speak briefly then of the waste, historically it's been divided into 3 groups. The high-level waste, in which the radioactivity level is 1,000 curies per cubic meter or more. There's an intermediate waste, and that one has a radioactivity level less than 1,000 but above 100th curies per cubic meter. And then the low-level one is less than 100th of a curie per cubic meter.
Okay, so just to review that, less than 100th, 100 to 1,000, and over 1,000.
Right.
Okay, and now we're going to be going to a break now, but just before we do, the below regulatory, less than 100th, is that equivalent to going out?
No, that's still too high.
It's still
the below regulatory concern is even lower. It's closer to maybe 1/100th or so.
A good day in the sun?
That's the new category.
A good day in the sun?
And these people claim that it can just be put in the regular trash. I personally don't agree with that view at all.
We're having a discussion today with 3 scientists from the nuclear industry, and I want to show you a book that you can obtain if you, at the end of the show, call or write me. I'll tell you how to get it. And it's a book that was written by one of our guests. It's called All Things Nuclear, and I've read it. It's shocking and very, very informative, and if you're interested, it'll tell you how to make a nuclear weapon, if you're interested. But anyhow, it is the absolute truth and the absolute facts about nuclear radiation. I highly recommend it if you're interested in this area. And I want to continue now with our discussion. Let's see who could answer this question. How much nuclear waste is produced by the commercial reactor business in the United States every year?
Yeah. Currently, the level is about 10,000 tons per year in the United States.
How many pounds? 10,000
tons.
Which is
well,
200,000 pounds.
Yeah. But
now,
remember, it's extremely dense material. These are the spent fuel rods. And although that sounds like a lot, by volume, it isn't really very much.
In other words, it would be, you could fit it into the space of a 4-car sedan, a 4-door sedan.
It would take more than that. But we could calculate it, but anyway.
Recent conversion was not quite right either.
Yeah.
10,000 tons is 20 million pounds.
20 million pounds,
Yeah.
excuse me. So that's how many pounds per citizen? Just curious.
20 million? Well, this would be a few ounces per citizen. We
Well,
have
10 citizens.
a tenth of a pound or so.
So that's something the government's making for me. I have a question. Of that 10,000 tons a year, right? Is that the right number? How much of that, or what percentage of that, gets lost or transferred to the environment accidentally or by waste? It can't be a perfect control.
Well,
some of it's got to get out.
These are big fuel rods. See, each one is about so big and maybe a yard long. You can't lose those easily, particularly when they're irradiating gamma rays like mad, and you could find one in a haystack as big as the ocean easily.
I think I have
no,
a picture
they don't get
of
lost.
those. I think I have a picture. Wait, this is.
Oh, yeah.
Here you go. This is.
Yes.
This is a picture of the baskets of fuel rod, right? Right, Jim,
Yeah, give it
in a
to Ken,
holding
will you?
tank.
Yeah, let me take that.
And those are the the fuel rods in their baskets being stored in water when they're removed from the reactor. They have to be stored in water.
So you're saying out of that generation of 10,000 tons of spent fuel each year in the commercial nuclear industry, there isn't any percentage that's lost in the environment?
Not at this stage. In the military program, however, where these rods are opened up and the material is processed to remove the plutonium, losses do occur there.
Well, how many pounds of, but they don't, you see, they wouldn't call it waste. They're turning it into weapons. Does the military...
After the plutonium is removed, what is left is the waste. And
how much
more waste than plutonium.
Well, how many tons of that is there a year, would you guess?
Well, so far as the plutonium is concerned, at the Rocky Flats facility, about 20 miles from Denver, Colorado, it is estimated that the amount of plutonium lost was about 65 pounds up in the ducts.
65 pounds, but
yes.
Plutonium is very dangerous. Plutonium?
Yes, plutonium oxide.
A gram of which, if you came in contact...
Well, yes, this is more or less purified now. You know, you could be near a gram of plutonium oxide without too much trouble.
Really?
See, remember, the fuel rods, although they contain the plutonium, what's giving off the dangerous gamma rays is partly the plutonium, but mostly the fission products, the other byproducts. Those are the dangerous materials.
And radioactive isotopes of common metals, mostly.
That are created, all right, well, in the military, all this waste that's created, how many tons of waste would you say? 65 pounds of plutonium.
Well, at the moment, there is accumulated more than 1 billion curies of waste. That amounts to about 40 million gallons of liquid waste from reprocessing. About 3/4 of that is in South Carolina at the Savannah River, and the remainder is at Hanford in the state of Washington.
Let's go, how many gallons?
About 40 million.
40 million gallons of contaminated liquid waste.
That's right. It's a sludge, really.
It's a sludge. What's it called in the industry?
Sludge.
Okay. I'll be sure not to order that the next time I go out to dinner. And how dangerous is that?
Quite dangerous. Not as much as these spent fuel rods. Now remember, most of this is aged. It dates from 50 years ago, during World War II. And so the more easily decomposed, or more rapidly decomposed materials, those with short half-lives, those have already disappeared.
But the sludge is still hot.
Still hot, very hot.
Well, if I got in a spaceship and went across the galaxy and came back 1,000 years, I came back 1,000 years from now, would this stuff still be hot, this sludge?
Yes, not nearly so much. After 1,000 years, it would be pretty tame by that time.
Well, if there's 40,000 gallons, how much are we producing each year?
Very little now. We're not reprocessing the military waste to make plutonium because we already have too much. So at the moment, there isn't more of this particular part being made. But we do have that 40 million gallons or 1 billion curies on hand, and it isn't stored well. It represents a potential danger, and we should address this problem. It'll cost a few $1 billion, but compared to the savings and loan scandal, that's nothing.